All right, party people. Well, the last few of you find a seat. If you can help me welcome Iryna and Oleh today. They are both data scientists and they're co-founders of the Dataforce solution. That's a company that specialized in delivering end-to-end data science and AI services. That's nice. And today, they're going to be giving us a tour of automated prompt engineering. So that looks fun. So let's give them a round of applause. Yeah?
Yes, thank you. Can you hear me, by the way? Yeah? Perfect. Yeah, as said, today we are going to talk about the automatic prompt engineering and try to answer the question whether the manual prompt engineering is dead. Before we continue, if you would like to follow the slides on your own devices, we have a QR code here. Actually, in the second part of the presentation, we have some rather small code snippets. They might be a bit too difficult to read on the screen, so please don't be shy, scan it. And while you are scanning, I will also do a very quick announcement. We have a bunch of data science-related stickers here. So please approach us after the talk to pick them up. We are also about to start working on the 2026 edition, so we need a bit of your feedback on which ones we should keep and which one to discard. Yeah, I hope everyone scanned the QR code, and we can actually start with the actual presentation. So why are we even interested in automatic prompt optimization? I guess it was hard not to notice that in the last couple of years, LLMs were a kind of big thing. Just looking at the NeurIPS 2024 poster presentations grouped by a topic, we can see that LLMs take up a substantial portion. But obviously, LLMs are popular not only amongst researchers, and we as developers also got a lot of cool tools, frameworks, and so on in the last months and years. Even major tech companies are stepping in with their LLM-powered offerings. I think you all know Apple Intelligence Suite, which provides native AI capabilities for iPhones and Macs. But when we look at how those things work under the hood, we see something like this: long, manually constructed prompts with directives like "do not hallucinate," "please provide your output in a certain way," and so on. So as the complexity of tasks performed by LLMs increases, it becomes clear that those tasks require complex prompts. And crafting those prompts is really not trivial. They need to be precise, well-structured, and non-ambiguous. Which naturally raises the question, can we actually optimize the prompt automatically given some training data? And the very short answer is yes. And with that, I would like to hand it over to Iryna, who will cover some theory on how it can be done.
Yeah, so before we proceed, we need to make a distinction between simple or single component and compound or multi-component systems. In single component systems, we typically deal with just one prompt. Think of a summarizer or a translator. There is one input, one output, and the prompt is pretty straightforward. Tuning that prompt manually is actually a manageable task. You write the initial prompt, tweak some things, and can already see satisfactory result. In contrast to simple systems, compound systems are made up of multiple components that are connected together in a pipeline. As an arbitrary example, imagine a retrieval-augmented QA system. Here, our program first retrieves some documents, then generates an answer grounded with those extracted passages, and then summarizes and rewrites the answer. Such multi-component systems are increasingly more popular nowadays, and there are a few key reasons for that. First of all, they often outperform monolithic models, especially when designed thoughtfully. In addition, because each module is isolated, we can inspect each step independently. Also, you know that different tasks don't always require the same horsepower. With compound systems, you can use different language models for different components. For example, you could use a cheaper and smaller model for extraction tasks and a more capable one for reasoning. This allows you to optimize cost-performance trade-offs more intelligently. Finally, such systems give you more ways to ground the model's output to some external tools or specific data sources. But here's the catch. This added structure comes at a cost. We're no longer dealing with just one model or prompt. Instead, we have a chain or graph of components, each with its own role and, more importantly, its own prompt. These prompts are no longer independent. For example, a change in the first prompt might slightly alter the output format, which would result in unintended and big effect in the later steps of the pipeline. Because of this cross-prompt dependencies, manual prompt optimization becomes infeasible. So while compound systems offer important benefits, they also introduce serious challenges in terms of prompt optimization. We already established earlier that there must be a way to approach prompt optimization like a machine learning problem, where we treat the prompt itself almost like a trainable parameter and optimize it based on some training data. But how exactly can we do that? It turns out that the simplest technique we can apply is few-shot in context learning. The idea is very simple. We just put several labeled examples directly into the prompt. For instance, to improve text classification, we can supply several text label pairs directly into the prompt alongside a very generic instruction. This way, we obtained a much better prompt without much handcrafting. However, here we have a single component system. Applying the same technique in a compound system is not that straightforward. That's because in multi-step pipeline, we usually only have access to the initial input to our AI system and to the final output it produces. But we don't have any intermediate input-output pairs between the modules. In that case, we can use training data and a teacher model to construct, trace, and save the intermediate results. These results can afterwards be used as few-shot demonstrations. This approach is used by a technique called bootstrapped few-shot. The idea is as follows. First, we run training inputs through our program. If the output is sufficiently high-scoring prediction as assessed by a specific metric, then we keep this trace. Otherwise, this trace is discarded. This process repeats until a maximum number of good or high-performing predictions is collected. Then these examples can be inserted into the prompt as few-shot demonstrations. Before we proceed with other methods, let us zoom into an important component of this process, the metric. The metric is what tells us whether a model's output is good enough to be saved as a demonstration. In simple cases, we can use traditional metrics, such as exact match, F1 score, accuracy, and so on. But most real-world applications don't produce simple outputs. Instead, they usually generate long-form text, for example, summaries, explanations, and so on. For these cases, we can use another language model to score or critique the outputs based on desired qualities, for example, correctness, tone, or even some domain-specific requirements like adherence to a brand voice. Let's now look at another method for prompt auto-optimization, which is called bootstrap few-shot with random search. It's based on the idea of bootstrap few-shot method we just explained, but it takes it one step further by actively searching for the best performing combinations of demonstrations. Let's go through how it works. First, we generate a set of good input-output traces using the bootstrap few-shot approach. Then, instead of just inserting these traces as demonstrations into the prompt, we randomly sample different subsets of these traces. Next, each sampled combination is evaluated, and finally, we select the demonstration set that leads to the highest validation performance. You might have noticed that so far the primary approach for prompt optimization was simply adding labeled demonstrations directly into the prompt without doing anything with the instruction. And it turns out that this method is quite powerful. Some studies show that optimizing just the demonstrations can lead to better performance than optimizing the instruction alone. However, the instructions become more important in tasks with complex conditional logic. Moreover, joint optimization of instructions and demonstrations generally yield the best performance. So how can we achieve that? One of the most well-known methods is called multi-prompt instruction proposal optimizer, or MIPRO. It is able to optimize both instructions and demonstrations at the same time. First, as in bootstrap few-shot, it uses a rejection sampling strategy to collect high-quality traces. Then, to propose instructions, MIPRO doesn't just rely on language model's internal knowledge, but it grounds the language model with some meaningful context. For example, summaries of the data set, overview of how the program flows from module to the module, bootstrap demonstrations, and historical information about the prompts and their evaluation scores. Finally, the best combination of instructions and demonstrations is found using a Bayesian optimization strategy. That is a powerful method because it allows to explore a huge space of prompts and instructions and pick the combination that works best together. However, MIPRO might still be limited in one key way. It uses a single feedback signal to optimize all modules. There is no direct or module-specific feedback. It makes it difficult to improve prompts precisely. The optimizer doesn't know which module is responsible for a poor performance. Making an analogy with the deep learning, it's like training a neural network without gradients. You just try different things and see what sticks. The concept that might solve this problem is textual gradients. Just like in neural networks, we could backpropagate those gradients to quantify how each parameter contributes to the overall loss and provides directions for optimization. Protege mimics this idea by using natural language explanations of what went wrong as textual gradients. It starts by running the current prompt on a mini batch of inputs. Then it uses the first prompt template that instructs the language model to describe problems which could have led to those mistakes. This response is our semantic gradient. It points in the direction of what is wrong. Then the second language model takes this feedback and edits the original prompt to correct these mistakes. This loop then continues recursively until the most highly performing prompt is found. TextGrad builds on the core idea of Protege, using natural language feedback to guide prompt editing, but it allows for systems of arbitrary depth and multiple trainable variables per prompt. According to some benchmarks, TextGrad can be on par or even better than Bootstrap few-shot with 8 demonstrations. Now that we covered some essential theory, I'd like to hand it over back to Oleg, who will walk you through available prompt optimization frameworks and more practical code examples.
Yes. Okay. You can hear me, right? Because I cannot hear myself for some reason, but OK. So when it comes to prompt optimization frameworks, without any doubts, the most popular one is DSPy by Stanford NLP. As their own motto says, it is used for programming, not prompting language models. And indeed, in DSPy, prompts are completely abstracted away through a concept known as signatures. A simple signature may look like this, which is just a string. Intuitively, by looking at it, we can understand that we want to have a certain question as an input and an answer as the output. In addition to that, the answer should be a floating point number. To test that it works, we can build a very simple DSPy program where we initialize a predict module with our signature and pass a question, what's the average weight of a cat, into it. We'll talk a little bit more about modules later, but for now, we can see that we obtain the answer 4.5, and it's a float. So our signature is working as expected. However, in some of the cases, expressing the whole signature as a single string can be a little bit challenging. For example, what if the inputs or outputs are not really self-explanatory and we want to add some additional descriptions, or maybe even explicitly set the initial prompt, the initial instruction. And fortunately, it can also be easily done in DSPy by using the class-based signatures. Here we have a more complex example where we want to check the faithfulness of the text given some factual context. The model should produce its verdict as a Boolean value, but also provide a list of supporting evidence. In such a signature, we provide an instruction as a docstring and the specification of the input and output fields as attributes. As you can see, the fields can also be provided with additional descriptions. So such a class-based signature can be used exactly the same way as the string-based signature would. And in fact, string-based signatures are internally converted into the signature objects anyway. But now you might be wondering where or how exactly those signatures are used under the hood. And in order to answer this question, we can look at the raw request that has been passed to the LLM. Here we can see that our signature got automatically converted into a rather long system message. It starts with the specification of inputs and outputs, then the description of the output format, and finally the instruction itself. So now, when we have the feeling how signatures work, we can actually talk a little bit more about the modules. So in DSPy, modules are basic building blocks. And if you have ever worked with PyTorch, you might find a lot of conceptual similarities. DSPy supplies several pre-built modules out of the box. Due to the time constraints, we won't be able to look into all of them, but let's have a glance at just two. We are already somewhat familiar with the predict module, which is the simplest one in DSPy. It just takes a signature and executes it without any modifications. A slightly more complex example is a chain of thought module, which ensures that the model produces some reasoning before the final answer by modifying the initial signature and adding an additional reasoning output field. So exactly like in PyTorch, we can also create our own custom modules. Here we built a chain that first translates the text and then summarizes it. So what do we need now to optimize this module. The final two components that we need are teleprompters and metrics. You're already familiar with the metrics from the first part of the presentation, and the teleprompters are somewhat similar to optimizers in PyTorch. Once we have a module that we want to optimize and a teleprompter initialized with a metric, we can simply call the compile method, which is the equivalent of fit or train. So to sum up, in DSPy, you would usually create your own custom modules using the pre-built ones as basic building blocks. You would also use signatures as abstractions over the prompt templates, and you would optimize your module using the teleprompter based on some supplied metric. The next framework we are going to look into today is TextGrad, which is also the official reference implementation of the TextGrad method presented in the first part of the talk. So unlike DSPy, TextGrad is relatively small and low-level framework and provides only a handful of primitives out of the box. First important concept in TextGrad is a variable, which is either a complete or a partial prompt that can also be optionally optimized by setting the respective value of requires grad. To use the variables, TextGrad provides a built-in black box LLM module that takes one variable for system prompt in the init and another one for the user message as an input. Now, in order to optimize the instruction, we use the same syntax as we would in PyTorch. First, we calculate the loss, where the loss in this case is just a feedback generated by a judge LLM. Then we call backward on the loss, and then step on the optimizer. And basically, this is more or less everything that you need to know about TextGrad. As I already said, it's very simple and intuitive, but some things cannot be easily implemented out of the box. For example, what if you wanted to optimize only a specific part of the prompt while hard-code the other, or provide few short demonstrations as you would in DSPy? Which brings us to the last framework for today called AdalFlow. Overall, it can be viewed as an extension of TextGrad, but with many elements taken from DSPy. Given that AdalFlow is a rather large framework and we don't have that much time left, we will not go through all of it, but only the most notable differences between AdalFlow and TextGrad. Firstly, in TextGrad, we had variables, and in AdalFlow, we now have parameters. But now we have two types of parameters: prompts to hold textual instructions and demos to hold few short demonstrations. These parameters can be used in explicit prompt templates. Hence, the prompt template can have both a dynamic optimizable part and the hard-coded static one. The functionality related to a certain pipeline can be also encapsulated in a certain component, which is equivalent of a module in DSPy. Finally, in order to optimize our component, we first need to wrap it into another Adal component, which expects the component we want to optimize and evaluation and loss functions. Then we can actually pass this Adal component to the trainer and call fit on the trainer. This might look a little bit too verbose, but at the same time, it's really not that different from what we have seen with other frameworks. So to sum up, AdalFlow is a very feature-rich framework that combines the ideas of TextGrad and automatic feature learning like in DSPy. But in my opinion, it's a little bit too verbose, which is not necessarily a bad thing, but at the same time, it might potentially imply a steeper learning curve. OK, so we covered some essential theory. We looked into the practical part and the framework, and now it's time to get back to the original question, whether manual prompting is dead. And as always, the answer is not that obvious. Without much doubts, the automatic prompt optimization brings many benefits. It is fast, it's simple to implement, and in many or even most cases, still cheaper than manual effort. Additionally, the optimization procedure can always be repeated in case the target LLM changes. However, there are also some potential limitations. First of all, the underlying prompt optimization procedure still depends on hard-coded, manually constructed meta-prompts. And those meta-prompts are not guaranteed to be optimal for your specific use case. In addition, by using the automatic prompt optimization, you are still bound by the reasoning power of the teacher LLM, which can be limited. Therefore, I would say it's probably a bit too early to declare the death of the manual prompting, at least for now. Yet, automatic prompting is a viable alternative, and we definitely encourage you to try it. And if you want to try it, but you don't really want to learn a whole new framework for that, at Dataforce, we have recently launched an open beta of our open source MLOps LMOps platform that also includes the no-code prompt optimization as one of the modules. It's live, it's completely free, and probably what's more interesting, it's 100% open source and the Apache 2 license. So you can access it through the QR code, and we would really appreciate if you try it out, provide your feedback, or maybe just start it on GitHub. And that was it from our side. Thank you for your attention. I'm ready for the Q&A. And please don't forget to pick up your stickers afterwards. Thank you.
All right, fantastic. So if you raise your hands for questions, I will send my runners to reach you.
Hi, can you hear me? The stickers look very nice. That's the first thing I want to say. Secondly, you mentioned abstracting away concepts of manual prompting throughout the presentation. And indeed, in the abstractions that we see, we also see a direction for that abstraction that feels like to me that is wrapped around the traditional concepts in traditional machine learning, like the gradients, optimization, even learning. And these analogies are nice, but we all know also that they are not exact matches. So my question is, in your opinion, as someone who worked with these things and maybe designed these things, do you think this is the direction of abstraction we should go while sticking with these traditional concepts, which makes things easier maybe, but do you see also other directions of abstractions which we would not constrain ourselves by connecting to these concepts which were used for other concepts of machine learning?
Yes, it's a very good question. And I would say it's really difficult to give a definite answer. Definitely for data scientists, it's much easier to adopt these tools when they have familiar abstractions. Obviously, there is no guarantee that those abstractions are the best. And to be honest, I wouldn't be surprised if in several years we'll see the emergence of new frameworks that adopt completely new concepts and abstractions. So hopefully, this answers your question.
Thank you very much for your presentation. It will be maybe a silly question, but what is the difference between using this automatic optimization of the prompt, then I just write a prompt that's what I want to say, and can you create a prompt for this task? And then I can iterate over time. So is there any such a big difference? Because in both cases, I'm using LLM to optimize my prompt, and in the description that I give, I am in control, but here, I don't know actually where it will go from the meta part.
Yeah, OK. So the main difference is obviously in the abstractions. So probably if you're working with deep learning, you could code everything, I don't know, in NumPy or even pure Python. But for some reason, we are still using those out-of-the-shelf frameworks. It's just easier. You can find more examples online. But obviously, if you want maximum control, you could do everything yourself.
Okay, we maybe have time for one more super quick question. No? Fantastic, guys. Okay, then I'll send you off to the next talk. Let's give a big round of applause for our speakers.
Don't forget about the stickers.
And don't forget the stickers.